Hello everybody, my name is Joanna Lesna and I'm an architect country working in Tokyo. I'm going to present a paper titled Degradus Program Heterogeneous Performance on Functionally Graded Biopolymers for Degradable Agricultural Shielding Structures. This research was part of my master thesis project I did a year ago in Copenhagen at the Royal Danish Academy of Fine Arts in Sita Studio. Architecture and building materials are often assumed to be everlasting, while temporary architecture is most often associated with the ease of disassembly and transportation. Materials and architecture components intend to be disassembled and reused, following the circular economy and sustainable concept of the closed life cycle. However, the waste management is currently a huge concern. If the life cycle of the products begins with the biodegradable materials, one doesn't need to concern about any potential recycling. Moreover, the matter of the material could be recycled not by saving the material, but by commanding the object to decompose into programmed particles or components that then can be reused to perform new functions. One of the significant contributors of the plastic waste production is an agriculture sector. The plastic membranes are used to cover the soil as a phenomenon called the plasticulture. New biopolymeric materials offer an alternative perspective of structures and systems that are programmed to disappear. Within an agricultural context, this implies structural life cycles that, after the seasonal use, return to nature and enrich the soil to grow their raw resources and use them again and again as a building material. And the societies, new design and fabrication perspectives which can create localized and sustainable in situ manufacturing process. The primary goal of the research employed an integration of the design process from the ground up by synthesizing material creation, digital modeling, robotic fabrication and assembly in a holistic approach based on the structure and optical demand of the agricultural shelter. Within this framework, several sub-questions have been investigated. Material-based design approach attempts to create a material which would degrade and through that be beneficial for the farmland, soil and agriculture. Likewise, this gives an opportunity to begin the process from the raw resources and make the bespoke design and construction process easy and affordable to everyone. On the other hand, this investigation undertakes the probe of decrease the overuse of material resources by the building construction sector and tests an approach of informing the digital model by the material properties data to build with minimal material and maximum performance. In this way, it obtains construction and assembly of the architectural parts in the most possible sustainable process, which includes use of the local raw materials and in situ fabrication. The research was initiated by an empirical experimentation of the material search. Fungal chitosan, agar-agar, and sodium alginate were mixed with water, acetic acid, and other additives in various proportions. By changing the proportion of particular ingredients, material sample resulted in diverse properties, like color, transparency, tensile strength, and elasticity. The key challenge of this investigation was to integrate the material composition and behavior with the digital modeling and fabrication, in the way that the form generation is driven by maximal performance with minimal resources through local material property variation. To obtain that, a multi-scale modeling approach was introduced. The design problem is decomposed into distinct but interdependent models according to the scales, and data is transferred between these models. It consists of three scales: material, pattern, and form. The investigation was based on a paired trajectories of material exploration made out of renewable and biodegradable resources available and abundant in every habitat on Earth. Advancement in tools and methods for in situ robotic additive manufacturing, development of the strategy for functional grading of the material properties to optimize the material distribution and reduce the building material waste. Following these constraints, methodology of the research was based on the circular design workflow where each phase informs another, which was a consequence of the ambition to connect an empirical material design with a formal architecture approach. The global shape of architectural membrane was found using a physics engine in mind to be reminiscent of typical membranes used on farmlands. The membrane was divided into the elements to simplify the assembling process, which were further generated by clustering the mesh points using the Kamin method. The elements were further partitioned using the algorithm that their edges were subsequently relaxed and developed into a specified pattern of customized panels for the sake of fabrication and assemblage. The functionality of the materials implemented in the system was investigated in two main directions: structure and light. That's why the structural performance of the global form and the solar radiation on a specific site were computationally simulated. The gradient of transparent at the bottom through yellow and red on the highest position on the structure was determined by agricultural purpose of the membrane, where red is considered as a color which attracts insects. The gradation of the material properties, rigid, pliable, transparent and solid, colorful, heavy and lightweight, is possible by combining the components with particle property in various proportions. This variability of the material distribution aims to create a complex and multifunctional body. Grading the materials was obtained by generating distance layers for specific functions. So 3 layers of customized patterns were generated for each panel. The first layer acts as a membrane, and it is specified by the distance to the ground. The upper panels are red, and the closer to the ground, the more yellow, white, and transparent the material becomes. The material grading on this level was achieved by creating one material composition per one panel. The composition was adjusted by changing the components, agar-agar, chitosan, and sodium alginate, in order to reach desired color and transparency. Additionally, the area of the edges contains more glycerin, which makes the material more flexible in order to enable sewing to assemble panels together. Next layer consists of load-bearing pattern, informed by the simulation of the structural behavior. Points on the mesh of the panels were grouped by the Kamin clustering method by the distance to the edges and structure behavior. On this base, a branching pattern with varying width was generated. Prior to the visual pattern, there was created a database which informs the robot about material composition. Chitosan differs between ratio 9 and 60% and agar-agar 2 to 6%. The higher the ratio of the both ingredients is, the stronger and heavier is the pattern. The final pattern is responsible for the solar radiation protection. Therefore, the pattern of this layer was created by grouping areas of similar radiation results of the simulation. For each of the areas, random points were generated with various density and connected with the shortest path. In this way, the created pattern was denser for the areas with the highest radiation results. As in the previous layers, prior to the pattern generation, the data for fabrication process was created. The material was extruded in liquid form through custom-made extrusion system using robotic arm. To determine gradient in a material deposition, it was crucial to investigate material composition, material concentration, and pressure variation. Working with the multiple material properties of functionally graded structures requires adjustable deposition setups. Because of multiple material compositions with various properties, refining the deposition setup, flow control, speed, and pressure needed to be considered. This was solved by testing chosen material compositions and applying an adjustable flow configuration to each of them. The intermolecular attractions of the particles in the wet water-based material allow to create a continuous graded system of heterogeneous performance which would not be able to achieve using other fabrication methods. The viscosity of the materials allows also for total self-bonding and self-repair of layers in a print. The fabrication process of creating a material from the ground up and deposition in a viscous state required properly controlled environment and the process setup in terms of production. Due to the viscosity of the material after extruding each layer, the following panels needed to be cured in an air pressure box under 40 Celsius degree to obtain quasi-solid state. The wet deposition of the biopolymer are under internal directional evaporation stresses while drying. This means it is very important to control the environment in the extruded artifacts while the evaporation process. After the panels were dried, they were assembled by sewing them together. This image of partially built pavilion. an early integration of performance parameters and fabrication methods into a threaded workflow will produce an integrated design process resulting in designs which embody their performative constraints and fabrication procedures. This project has presented a conceptual and methodological framework of a material-based large-scale design to fabrication process, implementing the customized biopolymer design to the real-world application of the temporary membranes with the circle life cycle in the form of seasonal agricultural shredding system. It shows a strategy of rethinking materials and the fabrication methods. Thank you very much for your attention, and please don't hesitate to ask many questions. Thank you.